Can you hear me online? No. Are we taking a minute or? I'm fine.
Maybe just walked out. She's the chair.
Oh, she's the chair. Okay, well, we can't start without the chair. We can't start without the chair.
Maybe she doesn't know she's here. Should I go check? I have chair, but I don't have my introduction ready for me.
It's a great pleasure to introduce Emilia Morosan from Rice University, who's going to give us this amazing talk on Kramers nodal lines, wild fermions, large anomalies, anomalous Hall effect in. Thank you.
Nice on fire. While I was sitting here in this previous panel discussion, which is a fantastic discussion, I changed my slides a little bit, so I included a few things in the beginning to talk about how do we make materials, how do we come to choose, and I'll tell you the real story behind how we choose some of the compounds, and then the story for, you know, funnies or the papers or whatever, right?
That's
so
great.
I'll have a couple of examples like that, but sitting there I thought, let's start here and be honest about how we do this, where not only be honest about it, but perhaps have the conversation in a way in which it's self-serving, but it also educates others to understand what it is that we're doing, right? I was only half joking when I said that Paul Canfield threw darts at the periodic table. I was a graduate student with Paul, and he's this great mind that designs materials, right? But because he was so fed up that people would accuse him of fishing expedition or throwing darts at the periodic table, one day he did come to the office, to the graduate student office, with a dart gun. And imagine that the periodic table was over there on that wall, and my desk was right underneath it. So I was ducking, and then he said, go make me that compound, whatever it is that he hit on the periodic table. Anyway, but that's not at all how he worked, and that's not at all how we work. There's many ways in which we come to well thought out experiments, whether they pan out exactly how we planned them or not. That's a different story, and I'm going to tell you a little bit about that. So some of you may have visited the posters, and then my student Yu Zhang talked about Kramers nodal lines in samarium aluminum silicon. So the story that I was planning to talk to you about today includes that compound, and then another one, an indium tantalum disulfide compound. If I don't get to tell you all about that, surely you've learned most of it from Yu Zhang already. But these are the key players. Yu Zhang is a graduate student in my lab, and Ximing, who was a research scientist in my lab. And we collaborate a lot with my colleague Ming Yi and her student Yichen. And then on the theory side, for this particular project, we collaborated with Vicky Law and his postdoc in Hong Kong. But here's where the story is going to go in the end. But this is what I just added while sitting in this panel. A couple of slides to say, how do we make materials and why? We do all these different growth techniques, and these are just some examples of things that we do in my lab. Why do we choose a particular compound? Well, in a lot of cases, people ask me, am I a physicist or a chemist? And I'm a physicist. I just have tools of chemistry to grow the compounds or to work on systems that I am interested in. What makes them interesting to me? Well, a particular problem. So I'll give you a couple of examples, but let's say for the talk today, we're interested in this Kramers vial unconventional fermions. I'll tell you how we come to choose compounds that are suitable for studying that problem. We're in an era now where we talk a lot about topology. I think at the beginning of this meeting, or at least the beginning when I got here on Tuesday, one of the first things that we were talking about was how we talk about quantum materials now as being correlated materials and materials with topological non-trivial properties, right? Well, 15 years ago, we did not have topology yet percolate the real material space. It was just a mathematical concept. I think we ought to ourselves to go back to look at all of these old compounds because we have this new lens of topology and we can unveil either new physics or maybe understand what at the time was mysterious or not understood. So not always do we have to make new compounds. We have to make the older ones maybe better. We can afford to spend the time and energy to improve the quality. Or we just look at older compounds with these new lens, either with looking for evidence for topology or whatever it may be, or maybe with new techniques, because now we have STM or ARPES or other spectroscopic techniques or other measurements, transport, very advanced, which we need to keep up with as they progress. And then we need to look at the materials, even the old ones. The new morphologies, right? Graphene has been mentioned several times. Carbon comes in all these different polymorphs, and yet carbon is almost a never-ending source of physics in some of these iterations. And then we do truly design and discover new materials. Failed synthesis or serendipity has been mentioned, right? We do plan for growth, but just because we mix together barium, iron, and arsenic, it doesn't mean that we're making, what was it, the 3,4,12, that was the initial goal of the iron nictide discoveries, right? When people mixed, not barium, but rather lanthanum, iron, and arsenic in a aluminum crucible with tin flux, and it was the tin flux that sucked out oxygen from the crucible, and then the compound that came out was lanthanum, iron, arsenic oxide, right? Something like that. So just because we mix certain elements, it doesn't mean that we grow exactly what we had targeted, and perhaps that's a good thing, because we can't plan for serendipity, right? That was what was one of the conclusions in the panel just now. And then there are unexplored phase spaces, and what I mean by that is for a lot of you who do synthesis, the phase diagrams are the maybe first order roadmap to where we are going. For those of you who don't do synthesis, just know that we have these guidance that comes from temperature versus composition phase diagrams, which for the most part is limited to binary compounds, very few ternary compounds. But beyond that, we just use our intuition and experience to just make new compounds that had never been made before in phases that had not been explored. So this is a little bit of a view of how we go about making compounds. Maybe why single crystals? Well, for this audience, perhaps I don't have to advertise why single crystals. But let me go on to talk about the approach of targeting the particular problem. So this is still the preamble before I start talking about Kramers von fermions. So I could tell you that when I was a postdoc in Princeton, I wanted to look for superconductivity in titanium diselenide. And so Bob Kava's mantra is, if it doesn't have copper in, put it in. It does have copper, take it out. So that's what I did. That's what I could tell you. But if I'm honest, I will tell you that we planned to look for spin 1/2 magnets. That's why we're using copper in a lot of the dichalcogenides. So at the time, I put copper and then iron and other things in a lot of dichalcogenides just to see what comes out. And what came out was this great result of superconductivity in copper intercalated TiSe2. In the same vein, I intercalated iron in various compounds, and no, it wasn't because I knew that I would get this unconventional magnetism or really large magnetic transport. It was just to see, actually what the motivation was that it was known that for some compositions, iron tantalum disulfide was antiferromagnetic, and for some other compositions was ferromagnetic. And what I really wanted to look for is a quantum critical point. That story didn't pan out, but great results came from looking at iron intercalated tantalum disulfide. And I have worked on this and related systems for maybe 7 or 8 years since.
Emilia, is this 1T or 2H?
2H. TIC2 is 1T, as you know very well, but no, this is 2H. We're now making a lot of decacogenates. If you want, we can talk about that, including 2H. And, well, I sort of included this over here, which was a story of doping in TIC2, different than intercalation, where we saw this metal to insulator transition with some amount of doping. Again, not something that I targeted, it was just serendipity, but great results came out of that study, and Vidya and I actually worked together on that some years ago. So for today's story, how does the samarium aluminum silicon and Kramers nodal line fit into this picture? Well, we targeted a particular problem, and I'll tell you that this problem of Kramers nodal lines and Kramers vial fermions has to do with crystal symmetries, and so the choice of material was motivated by the crystal symmetry, which was predicted to show this kind of physics. And so that's how we arrived at samarium aluminum silicon. While doing that study, the serendipitous discovery was that a very large anomalous Hall effect, both in the antiferromagnetic and the paramagnetic state. So this is pretty much the outline of what I had initially planned to tell you today. So let me see how much I can get through. I'm happy to just talk to you and pause for questions as I go through this. I'll start with Kramers nodal lines and Kramer vial fermions in the samarium aluminum silicon type family, with particular focus on this compound. And this fits into the bigger picture of topological materials and different flavors of topology or correlated topological systems, which come about, as we see almost every day, because of breaking of different symmetries or because of different crystal structures, etc. And at the other end, they tend to have different functionalities, different optoelectronic responses or responses to electric and magnetic fields, etc. So we all find that they have great potential for different applications, and if nothing else, just for understanding some novel fundamental physics. So with this, I'm trying to advertise the need for looking for new types of topological systems, new types of unconventional topological fermions. And so one place where we can look are these Kramers vial fermions that are said, theoretically, are predicted to be universal to non-magnetic chiral structures in the presence of spin-orbit coupling. Let's see if there's a pointer. Okay, so these Kramers vial fermions are predicted theoretically to be a universal feature in chiral structures with spin-orbit coupling. And what they are, they're these degenerate points that are pinned at high symmetry points in the Brownian zone, as I'm illustrating here schematically. If we now move to achiral crystal structures with spin-orbit coupling, these Kramers vial fermions become degenerate nodal lines. For example, over here between the gamma and A points in the Brownian zone, you see these lines are degenerate, and then they are non-degenerate away from that particular line in the Brownian zone. And so what they are, these Kramers nodal lines are lines, doubly degenerate lines connecting these time reversal invariant momenta, these high symmetry points in the reciprocal space. And so coming back to the motivation of where do we look for such physics? Well, let's look at achiral non-central symmetric crystal structures. And theoretically, again, the prediction goes further to say that there are two types of Fermi surfaces that can produce these Kramer nodal lines, the so-called spindle, which in a cut across this Kramers Weil nodal line can have something like a Rajba-splitting, or a knockdown, which looks like this, which has these Dirac points, or Dirac fermions. The other interesting thing about this Kramers nodal lines is that with some tuning, for example, with strain or breaking the mirror symmetry, you can actually split the degeneracy of the Kramers nodal line, and what you end up with is you go from Kramer nodal line to Kramer Weil fermions, which are, like I said, pinned at high symmetry points. So there's great potential for interesting fundamental physics, then also for perhaps functionalities and properties. So if we are,
So
yeah,
why you call it Kramers-Weil point? What's it mean? I mean, can you apply perturbation to break, open up the gap?
at the
Because
three,
yeah, I mean, typical Weil point,
So
it's
there-
not Kramers, it's not degenerate.
but this is not the same, the origin of this isn't the same as the band folding in just the Weil semimetals. They come about because of this symmetry enforced or pinning at this time reversal layering momenta at this high symmetry points. So they're not the same as the Weil points in
So I'm saying that this, why not call it drag point if it's doubly degenerate instead of just Weil?
But it's not doubly degenerate, it's,
At that point, it's doubly degenerate.
at that point it's doubly degenerate.
It breaks inversion.
No, it comes about from breaking time reverse.
It has a Kramers degeneracy at one point, and
Yes.
it broadens out into
Yes,
a Weil
it
cone
broad-
around it. So
Yes,
you don't want to leave anyone behind to include Kramer, and you
I
include
guess,
Weil.
I guess that's
That's the reason.
and it is distinct
Yeah.
from just the Weil.
Time reversal symmetry pins it to be at that.
Time reversal symmetry pins it, time reversal symmetry pins it at this, what are called trim points, yeah. So because I said to look at achiral structures, samarium aluminum silicon is a family of compounds that had already been studied quite a bit. As you can see here, many papers, and probably this list is by now incomplete. But the point of all of these studies was revolving around Weil fermions and Fermi arcs, anomalous Hall, singular magnetic resistance, etc. No talk of these Kramer nodal lines or Kramer unconventional fermions. And so because the crystal structure fits the bill of the theoretical prediction, we wanted to see if that pans out. And so my student Yu Zhang grew these signal crystals, and then we collaborated with Yichen and Ming to do RPES. So let me tell you a little bit about what we found. Here's the band structure without spin orbit coupling, where you might not be able to see exactly what I'm after, but let me toggle back and forth between the band structure with and without spin orbit coupling. And what you notice is that the bands are two-fold degenerate nearly everywhere except along the gamma Z line with spin orbit coupling. So the gamma Z lines remain degenerate even with spin orbit coupling, while the degeneracy is lifted everywhere else. So here's the RPES that shows this point moving up in energy. As you do, I should point out that this degenerate line is along gamma Z, and if we do cuts in RPES in the orthogonal directions along the gamma sigma X, as the energy changes, you see this point moving up at the gamma point. And then comparison of soft X-rays RPES with calculations showed this Kramers nodal lines and good agreement between RPES and theory. Then we moved on to characterize the Weil fermions in this compound, where here the top row shows the RPES data with the theoretical calculation overlaid for the bulk, and then the bottom line is the surface calculation. And so there are 56 Weyl points that are predicted to exist in this compound, and then this is what you would expect the Weyl points to look like in reciprocal space. So we then complemented the ARPES and the calculations with quantum oscillation measurements. And so sure enough, we observe large quantum oscillations. Here's the Shubnikov-de-Haas oscillations is a function of a field for different angles of the applied field relative to the crystal direction. And so when we map that with the calculation, we see good agreement for these, what I'm calling alpha and beta pockets, which are some of the predicted Weyl points that I showed earlier. So altogether, with ARPES and quantum oscillations and DFT, we were able to paint a picture where the experiment and theory agreed of these Kramers nodal lines, which then turn into, or with Kramer-Weyl fermions, when we break time reversal symmetry. And maybe I haven't told you anything about the breaking of time reversal. I don't know how much long you want me to talk. I know that we started a little later.
You can go on until 12:05.
12:05.
Yes,
Okay. Maybe
but with questions.
yeah. So maybe I don't need to take all this time to talk. I can stop at any point. I'll just move on to just briefly tell you about the large anomalous Hall effect that we discovered in samarium aluminum silicon. We found this both in the antiferromagnetic and in the paramagnetic state. And what the punchline here is that we are proposing a new model to explain the large anomalous Hall in this particular compound and in this class of compounds. And the new model is based on field-shifted Weyl nodes in this non-central symmetric crystal structure. So what this basically means is that in the absence of an applied magnetic field, so with time reversal, the Weyl nodes sit at opposite momenta in reciprocal space, such that the chiral, the Chern number is 0 everywhere in the Brun zone. But when you apply a magnetic field, the Weyl nodes, the existing Weyl nodes, are shifted such that they're no longer at opposite momenta in reciprocal space, and this gives rise to non-zero Chern number regions, and that is what creates the Berry curvature, which in turn is responsible for anomalous Hall. And so the motivation for this, again, I have to be careful. Do I tell the true story about how we came to this, or is it the sales pitch? And in reality, was that we were looking for Kramer-Weyl physics in this compound, and then we observed the anomalous Hall, and then we had to try to explain it, right? And we knew at the time that it was easier to understand anomalous Hall in ferromagnetic systems because it comes about from the spontaneous magnetization, the local magnetic field. But there are so there are several ferromagnetic systems where anomalous Hall is observed, but there are also a few antiferromagnets where people have reported anomalous Hall effect, and yet neither one of those pictures, and in the interest of time, I'm going to go a little faster over this, but neither one of those pictures really fit the bill for samarium aluminum silicon, and that's what motivated us to look somewhere else or try to come up with a new explanation. So here's what we observe in samarium aluminum silicon. This is just a summary of the low temperature data, which includes, let's see, the black curve is a derivative of resistivity, the red curve is specific heat, and the blue is a derivative of magnetization, all pointing out to the magnetic order below 11.5 Kelvin, and then a spin reorientation to the lower temperature. But now when we look at all data up to 14 Tesla for different temperatures, starting from low temperature blue over here, increasing through the magnetic order, the anomalous Hall is still large, both in the antiferromagnetic state and the paramagnetic state. It's maybe easier to see if we convert to conductivity, and that's what I'm showing here, where I'm illustrating here with the black line how we account for the normal conductivity in a two-band model for this particular compound as our best estimate of the anomalous Hall contribution. And so when we subtract that normal Hall estimate, what we end up is with this manifold over here, the conductivity as a function of field for different temperatures, where there's a large peak that's centered more or less around 1 Tesla, and then somewhat, and that persists, like I said, all the way from, let's see, the lowest temperature here is 1.8, all the way to 100 Kelvin, which is way above the magnetic ordering, right? Yeah.
Why could you call this as anomalous? You have a magnetic field. You have a magnetic field, why you call this anomalous?
Because this is an antiferromagnet.
Yeah, but still, why you call it anomalous? You apply magnetic.
Well, the normal field, the normal two-band model will give you just this. So the
No,
normal.
but that's without magnetism, right? So
There's some old, yeah, there's the debate, like, so it's a spontaneous versus anomalous.
Well, it's
You're
not
saying there's no
spontaneous.
spontaneous.
It's not spontaneous. It's not spontaneous because it doesn't happen at zero field.
Yeah, many people share that definition, but there's some language variant that some people use anomalous.
Anomalous is by definition, that's how, Hall studied. Anomalous means spontaneous.
I think, okay,
There's two
by
meanings.
spontaneous, I think spontaneous, I think, my understanding is what's referred to as H equals 0. At least that's correct.
So in other words, yeah, it should be exactly, so it's spontaneous. Anomalous should mean spontaneous, in other words, without magnetic field. The only thing you do with magnetic field should be controlling
Okay,
the
so
domains.
let's just say this, let's just say there are different contributions to the Hall effect. There's the contribution which we seem to understand that comes from the carriers, from the bands. And then there's other contributions which, as I'm aware, are referred to as anomalous and
Okay,
topological.
I have a chair's prerogative. We can discuss definitions later.
But
Please go ahead.
just for clarity, this is the contribution that's not accounted for by any theoretical model, simple model based on band theory, okay? So that's for the purposes of this discussion that I'm going to refer to as anomalous. Yes?
Just your top left plot, the conductivity goes negative. Is that like unsymmetrized in plus and minus
It is
field?
unsymmetrized.
Oh, and then on the right hand side is symmetrized with the same data.
Let's see, is that?
That is also conductivity. And
Yeah, but is it
that is
symmetrized? I
anomalous.
don't think it's symmetrized either.
It is symmetrized. It's like with temperature, we are growing as electron carrier is slightly increasing, so that you is at low field you see like negative. It's just changing of normal.
So is this symmetrized?
Yes, that is.
Okay.
Yeah.
I guess I need to.
Anti-symmetry.
Changing of
Different.
carrier concentration mobility.
Anti-symmetry.
plus temperature.
Yeah. Okay, thank you.
All right, so what I wanted to say is that for the purposes of this discussion, what I'm looking at is the extra contribution to Hall that is not accounted for by band. But what's important for the point I'm trying to make is that even though magnetic order happens below 10 Kelvin or 11 Kelvin or so, and we see some enhanced contribution from the Hall conductivity at very low temperatures over here, you may notice that this actually stretches out, as I showed in the previous plot, stretches out to high temperatures. And so it goes all the way from the antiferromagnetic state to the paramagnetic state. And to some degree, this contour plot over here is similar to, I don't think I have a plot of the gadolinium platinum bismuth, but it's very much like what was observed in gadolinium platinum bismuth. But I think that
Video.
5 minutes.
the behavior,
She started late.
I know, that's because everybody started late, but
No, she gets
oh, I'm
5
happy
more
to,
minutes.
I'm happy to stop and then just have a discussion if we want to talk about it. Then I'll just go to the indium tantalum disulfide and just show you that in addition to Kramers vial physics, we also found superconductivity here. So this brings us to a question of whether superconductivity and the Kramers vial physics are entangled. But I'm going to stop here and then happy to take questions or have some more discussions.
We have time for questions. She started late, so please.
One question, is this in the antiferromagnetic field, is it collinear or not collinear?
I don't think that we are very clear on what the magnetic structure is. The neutron diffraction is, experiments on samarium are not easy to do because of the absorption of samarium. There is neutrons, we've done it, and there's already a paper before us that reported neutrons. I don't remember if it's collinear or not, but it's definitely coplanar. There's no spin texture. That's what I think I can say for sure.
This is just related to the magnetism. Sometimes, you know, even in the paramagnetic state for samarium, it's weird.
Yeah.
So is this
Because
one of the
crystal
ones
field-
that's looking really like a Curie-Weiss temperature dependence? or
Up
is it-
to not the highest temperature, up to about 150 Kelvin.
I see, and then
So then
some other-
the crystal field comes in, yes. But up to about 150 Kelvin, if I recall correctly, it does look.
Do you know what the effective magnetic moment is?
I don't remember.
You know what the valence of the samarium is in this?
3+.
Not mixed valent.
So because we don't have a large range of Curie-Weiss-like behavior from which I can determine the effective moment very accurately, the bit that I can fit tells me that it's 3+.
Could you do core level spectroscopy?
Probably. We haven't done it yet. Yeah.
Actually, I think RPAS dissolves the samarium surplus bands.
ARPAS, this is something that came out very recently from Ming's group. They do see a small amount of 2+ from ARPAS, but it's primarily 3+. So, yeah.
There's a whole series of these rare earths that
Yeah.
are 3+ aluminum silicon, right?
Yeah, neodymium, I think
That
from
would be
what I
quite
know.
a difference. Like, okay, we can talk about it.
Neodymium is probably one of the better studied ones on this. Colin.
So is there a reason samarium would not be 3+ here?
Well, samarium is different than neodymium. Samarium is special in the sense that it has low-lying crystal field, and so.
Just chemically, it's in the same bonding and, well,
Has a smaller ionization.
Yeah, but
just-
even though chemically it's the same bonding in the same crystalline environment, etc., rare earths are similar to a degree, but especially for light rare earths, they tend to be unique and not as similar as the heavy ones are.
But if it's not 3+, you should see some anomaly in the last parameter.
Yes.
well, that's what I mean. Is it there or not? If it's just in line with the other rare
It's
earths.
pretty much, so, you know, to within error bars is falls in lines with the lanthonide contraction, but a small deviation from 3+ will not throw you off that.
Okay,
Enough.
last burning question. Okay, go ahead.
So can I ask the role of nodal line? For instance, nodal effect naively can come from 1 point. So for instance, if integration of the wildlife very curvature for nodal line, is there contribution or just doesn't know the role of that for anomalous effect?
For anomalous fall.
Yeah, the nodal line too.
So we believe that the role of that is based on this model. Let me see if I can get to it, where you're shifting the vial points, the existing vial points. That's the difference with some of the other systems where in H=0 in this compound you already have vial points, in some of the others you don't. So it's the shifting of the vial points at non-opposite momenta, and the fact that you're now creating this non-zero chiral regions.
Okay, I think we have to stop now. Thank you very much, Emilia. Our our next speaker is